Hello and welcome to Diplomatic Derivatives, a platform where we'll dig deeper into the world of pure mathematics and international relations, seeking to excite your curious minds. This channel is created with the ultimate aim to make complex concepts easier and fun. We begin with pure mathematics, where we'll be diving into modern algebra, calculus, and analytical geometry, along with complex variables. So today we begin with understanding the group theory. On our screens, we see the Rubik's Cube and a snowflake. Well, the reason for putting these images on the screen is simple. We see from solving a Rubik's Cube to the symmetry in the snowflakes, there is a structure, there is a process involved, and that's explained through the group theory. Well, actually the group theory is all around us. But don't worry, this isn't going to be a lecture full of scary symbols that's going to complicate the entire scene. In this video, we'll break it down into simple ideas, relatable examples, and zero stress. So if you've ever been curious about structures, about patterns, you are in the right place. Let's simplify the group theory one concept at a time. Alright, so we begin with the very basic definition of what group theory is. Group theory is a branch of mathematics that studies symmetry and structure. Now we see symmetry and structure all around us. That's why this theory is so important. It will basically explain how the symmetry works, how structure works. We are going to dig deeper into these two concepts. It helps us understand how things can be transformed, moved, or rearranged without changing their essential nature. Now, what's important to understand here is that we see things around us. Now, these things, there can be actions done on the things. For example, those things could be transformed, those things could be moved, or those things could be rearranged. But what is the condition? Without changing their essential nature. So for example, we have a pen. A pen is going to stay a pen no matter what happens to it. So either this pen can be opened, the cap can be removed. You can either move it up and down, you can write with it, but the essential nature of it, that it remains a pen no matter what action is performed on it, right? So that's what group theory is talking about. Just explaining with a very basic example. We see symmetry in these shapes. For example, if you have a square, there are certain lines of symmetry. Certain actions could be performed. For example, if this is the axis of symmetry over here, we can either flip it over here, make it a rectangle. We can maybe move it along this axis of symmetry to make it a triangle. But at the end of the day, these are all the actions performed on a square. Okay, and square is a shape. So what action we perform, no matter what the action is, the result is going to be another shape, right? So these symmetries that we see all around us all are a part of the group theory. So before further going into the group theory, first we understand what a group is. A group is a set of things, like numbers, moves, or objects that you can combine or do something with, but in a way that follows certain rules. Now, as we talked about in the previous slide, when we said that there are things and there can be action that can be performed on those things, for example, transformed, moved, and etc. etc. When we come to specific mathematical terms, we see in maths, a group is a set of things. Okay, so that things from the previous slide is basically a set of things. For example, we have numbers, we have moves or objects. Okay, and what actions you could do on it, you can either combine it or you can do something, whatever the action is. Either you can add numbers, you can subtract numbers, whatever the action is. Okay, but in a way that is now another the condition over here is in a way that follows certain rules. So being inside those rules, there are certain actions that could be performed on certain things, right? And if this entire condition is justified, that particular set will be called a group. Okay, so we will understand it slowly. A group must follow 4 rules. So for something to be called a group, there are 4 rules that are supposed to be fulfilled. Number 1, closure. If you do one move, then another, this result is still a part of the system. We understand the group theory, we understand what a group is and why something is called a group with the help of the 4 rules. And the first one being the closure. we are going to apply it on this particular puzzle over here. So we see we have a puzzle where we can move the numbers, and we have to basically complete the puzzle. Now this process is going to be a group. Why? Because the property of closure is satisfied here. If you do one move, right, the next move that is going to be a result after the first move is going to be a similar move, right, which is a part of the system. Therefore, the system is closed under this action. Okay. Second is associativity. It doesn't matter how you group the moves. So you either do 6 down, 5 right, and 4 right. You can either go back and do another means. You can like find another means of doing a similar kind of a move. You reverse the moves. Okay. No matter what the grouping is, the result is going to be the same. Okay, that's associativity. How we do normally with addition, we say a plus b plus c is equal to a plus b plus c, right? So that associativity is also fulfilled. Next, we have the identity element. That is, there's a special move that does nothing. It leaves things unchanged. You do nothing with the puzzle, it remains as it is, still a part of the system. Inverse element, every move has an undo move. That is, if you move 6 up, you can move 6 down, and if the result is still a part of the system. So if these 4 conditions are fulfilled, that is closure, associativity, identity element, and inverse element, and every answer that you receive is part of the system, therefore the set is a group. Okay, so now we have seen what are the 4 rules of the group theory. Now we're going to see how in a real life example this group theory is employed. We see a Rubik's Cube on the screen. Now there are certain processes, like for example, you combine, you twist, you turn, you do multiple things with the Rubik's Cube, and at the end you get a completely solved Rubik's Cube. How is it possible? It's possible because there is a pattern and structure at play, and the people who solve the Rubik's Cube in a matter of seconds, they know how to solve this, how to solve the pattern. They know how to solve this puzzle in front of them. It's a part of the group. Whatever move they do is still part of the system. Whatever the way they combine the steps is going to be part of the system. There is do nothing move. You can either do something and then reverse it, right? So it's still a part of the system. Therefore, if 4 rules are satisfied, it's part of the system and it's a group. And groups can be solved off. Obviously, you can solve a group, right? Therefore, we say the Rubik's Cube is solved with the help of the group theory. The group theory is working in the real world, we are going to understand its mathematical formation, how mathematically we represent groups, and how we work with the groups. So a group is a pair, G star. Now this is the mathematical notation of a group, where G is a set of elements and star is a binary operation, like addition or multiplication that combines 2 elements of the sets and returns another element of the same set. So this could be either addition, multiplication, and whatever the operation according to the group. Okay. For example, we have a group Z plus. Now Z is basically the representation for integers, and this plus over here tells us that it's a positive group. Okay, now this plus is not to be confused with the operation over here, because this operation is the operation to be performed on the group, but this plus here is talking about how what the set itself is. For example, we know integers on a number line, so we could just draw a number line, right? And we have a 0, and on this side we have all the positive integers, and on this side we have all the negative integers. Now if you just write Z, we know we are talking about the entire number line, but when we add a plus here, we say that we are only talking about the positive integers, and we exclude the negative side and 0 as well, because 0 is neither positive nor negative. So this is basically just talking about a positive integers set. Okay, now on this there is an operation which we are applying, and that operation is addition. Okay, so we apply addition on this positive integers set. Okay, so for example, we take 2 and we take 3, so 2 plus 3 is going to give us 5. Now this answer that we get here, 5, is element of Z plus, obviously because it's a positive integer. So therefore we say that this set is closed. This set is closed under addition. Okay, so now what we're saying is that the first rule of closure is accepted here. It's satisfied. So this is a group under this operation. Now we did not apply the rest of the 3 rules. We have to ensure that all the 4 rules are satisfied. Only then we can call it a group. So this is just an example of the first rule. Okay. Go through the rules again. So we have closure, the first rule, which is closure. For all a, b element of G, a, b are the elements of the set G. That set could be integers, natural numbers, real numbers, rational numbers, or anything. The result a dot b means taking any 2 elements from the group. We will perform the operation. So this is basically, this operation could be either addition or multiplication or whatever. A star b is also in G. So the answer of this particular operation must also be a part of the group. Then we say that it's satisfying closure. If you add 2 integers, you still get an integer. So it's part of the integers group, integers set. So it's closed under that operation. Next we have associativity. Associativity is always true for addition. So any elements, we take 3 elements from the group, we perform the associativity operation, and it's satisfied for addition. Okay. Identity element. Now there exists an element E, element of G, such that for every element, for every A element of G, A star E is equal to E star A, which is equal to A. So what we are saying is that we have a set, and in that set we have, for example, we have an element 1. Okay. Now we say that the set is for multiplication. I mean, the operation we are going to perform is multiplication. So we take any other element from the set. For example, we are taking 2. Right. Now for checking for identity, what we do is we take 2, which that is any element from the set. The operation is multiplication, so we take multiplication and we multiply it with 1, which gives us 2. So this means that 1 is the identity element, as it returns the same element in the set under this operation which is mentioned. Okay, so therefore 1 is the identity element for multiplication, right? If the identity element exists, therefore the set is a group. Okay. For example, we are talking about addition, so we have 0 is the identity element in addition, because any element added with 0 will give the same element. Next we have inverse. So for every A element of G, there exists an element A inverse element of G, such that A into A inverse, A star A inverse is equal to A inverse star A, which is equal to E. That means for any element, for example, if we are talking about multiplication, we have 2, right? So 2 multiplied by 2 inverse is going to give us 1. We get the identity element, right? So under this operation, when the element with its inverse is multiplied, we get the identity element. Therefore, this inverse exists. Okay, so if we're talking about addition, we are going to get the additive inverse. So we will have 5 added with minus 5 will give us 0. Okay, so we get the identity element of addition, therefore inverse exists. Okay, so that's basically about the 4 rules. Some of the common examples, very basic examples. We have the integers under addition. We have the integers. Now we do not see a plus over here on top of z, therefore it's all integers. Okay, so we have 0 plus minus 1 plus minus 2 plus minus 3 and so on. Set of all integers, and operation is addition. So this plus over here tells us that the operation we're going to perform is addition. Okay, and this set is a group under addition, satisfies all group axioms, therefore it's a group. We will be proving all of these things in the future videos. Then we have a non-zero real numbers under multiplication. This set is, what we are saying is non-zero real numbers under multiplication means all real numbers except 0. So we have all positive real numbers like 1, 2.5, root 2, pi, etc., and all the negative ones, minus 1, minus 0.01, etc. Now this real numbers group is under multiplication. A dot means multiplication, also is a group. All 4 rules are satisfied. Okay, that's it for the video. I hope everything was clear. I tried to make things as simpler as possible. That was all about the group theory, the very basic understanding of a group theory, the 4 rules to be applied for something to be called a group, and the common examples of group. I hope it was all simple to understand. I hope the complex concepts were made simpler. If you have any questions related to the groups, to the group theory or the group itself, or the rules or the examples, or how to solve the examples, we will definitely be doing things in the future videos. But still, do ask in the comment box below if you want something else to be understood. Don't forget to like, share, and subscribe. In the next video, we'll be jumping towards these subgroups, and then future we'll be talking about cyclic groups, homomorphism, automorphism, etc., etc. So that's all for today. Thank you, and don't forget to tune in for the next one. Bye bye.